High-speed rail trains, a game changer or nightmare? High-speed rail (HSR) technology has evolved to minimize track vibrations and misalignment, primarily through the use of persistent welded rail. The majority of high-speed rail lines are electrically driven via overhead cables, incorporate in-cab signaling, and deploy advanced switches with low section and frog angles. One innovative approach is the road rail parallel format, which positions railroad lines adjacent to highways. Notable examples include the Paris-Lyon and Köln Frankfurt routes, where a significant portion of the track runs parallel to highways, offering a unique integration of rail and road infrastructure. Track sharing is a feature observed in China, where high-speed lines operating at speeds between 200 and 250 kilometers per hour may cater to both cargo and passenger transportation. However, lines with speeds exceeding 300 kilometers per hour are exclusively reserved for passenger CRH trains. This flexible approach allows for efficient utilization of the rail network, demonstrating the adaptability of high-speed rail systems to diverse transportation needs. The technological foundation of high-speed rail involves advanced applications of standard gauge rail technology. By constructing a new rail infrastructure with 20th-century engineering principles, including the elimination of hindrances like at-grade roadway crossings, frequent stops, and a series of curves, higher speeds in the range of 250 to 320 kilometers per hour can be sustained. The total cost of ownership for HSR systems is generally lower than competing alternatives, such as constructing new highways or expanding air travel capacity. While Japanese HSR systems tend to be more expensive than counterparts, they offer comprehensive features such as dedicated elevated guideways, absence of traffic intersections, and disaster monitoring systems. Notably, the higher costs associated with Japanese systems often stem from the construction of tunnels through mountains, a characteristic shared with the Taiwanese HSR system. Recent advancements in wheeled trains have pushed speed limits beyond 400 kilometers per hour, incorporating innovations like tilting train sets, streamlined designs to reduce drag and noise, air brakes, regenerative braking, more powerful engines, and dynamic weight shifting. European high-speed rail routes often blend sections of new track, where trains operate at full commercial speed, with segments of older track on the peripheries of the route, particularly near cities. In France, cost-effectiveness is achieved by adopting steeper grades instead of constructing tunnels and viaducts. However, in Switzerland, where hilly terrain is predominant, tunnels become inevitable. Given that these lines are dedicated to passengers, gradients of 3.5% are employed, exceeding the previous maximum of 1 to 1.5% for mixed traffic. Investing in potentially more expensive land to build straighter lines proves beneficial, minimizing construction, operating, and maintenance costs. In contrast, some countries have developed high-speed rail without these cost-saving measures, allowing the railroad to support other activities like cargo transportation. However, the coexistence of trains with significantly different speeds on the same line results in substantial decreases in overall line capacity. Freight high-speed rail services are a rarity globally, as high-speed trains are primarily designed for passenger transportation. An exception is the French TGV La Poste, a high-speed mail service that operated between 1984 and 2015, reaching a maximum speed of 270 kilometers per hour. In Italy, Mersitalia Quick introduced a high-speed cargo service in 2018, utilizing converted ETR 500 passenger train sets to transport goods at average speeds of 180 kilometers per hour between Caserta and Bologna, with plans for network expansion throughout Italy. China Railways has also ventured into high-speed rail freight, partnering with SF Express to transport packages using dedicated train segments alongside regular passenger services. High-speed rail, HSR, presents a formidable challenge to the traditional notion that air travel, with its faster speeds, invariably results in quicker overall journeys. It's crucial to unpack the advantages of HSR comprehensively. Despite airplanes achieving higher speeds, the total time spent on air travel can be significantly extended by a multitude of factors. These include the time taken to get to and from often distant airports, the check-in processes, luggage handling, security procedures, and the boarding process. The cumulative effect of these factors not only increases the time invested in air travel, but also contributes to higher costs for passengers. Conversely, high-speed trains become a preferable choice for short to mid-range distances. Rail stations are frequently situated closer to urban centers than airports, providing a natural advantage in terms of travel time. This is particularly relevant for densely populated urban areas, where airports tend to be located at a distance due to land scarcity, short runway restrictions, building heights, and airspace issues. The closer proximity of rail stations eliminates the need for lengthy travel to airports, offering a more time-efficient option for travelers. Furthermore, rail travel exhibits a distinct advantage in weather dependency. Unlike air travel, which is significantly affected by adverse weather conditions leading to cancellations or delays, well-planned and operated rail systems are more resilient. They can withstand severe weather conditions such as heavy snow, fog, and major storms, ensuring a more reliable mode of transportation. This reliability contributes to a reduction in travel disruptions and increased passenger satisfaction. Comfort is another noteworthy advantage of high-speed trains. Passengers on trains have the freedom to move about the cabin during the journey, enhancing the overall travel experience. This stands in contrast to airlines, which often have intricate algorithms aimed at minimizing weight to save fuel or to meet specific runway length requirements. Rail seats are less subject to weight restrictions than those on planes, contributing to a more comfortable and flexible travel environment. Delays, a common concern in air travel, are mitigated in certain high-speed rail routes. Trains are less likely to experience delays due to congested airports, especially in regions where HSR has historically proven most effective. Unlike airplanes at crowded airports, a delayed train does not have to wait for another slot to open up, enhancing the reliability and punctuality of high-speed rail services. Additionally, some airlines view short-haul flights as economically unviable, leading them to rely on high-speed rail for connecting services, further reducing the likelihood of delays. De-icing, a time-consuming necessity for planes, is eliminated in the case of HSR. This process, while essential for aircraft efficiency and safety, involves aircraft staying on the ground, incurring hourly airport fees, occupying parking space, and contributing to congestive delays. High-speed trains, not being subject to de-icing requirements, contribute to operational efficiency and reduce travel downtime. Noise and pollution are significant concerns associated with major airports. These hubs are known to be substantial contributors to pollution, with particulate contamination often doubling downwind of airport areas. Rail travel, especially when powered by renewable energy sources, provides a cleaner alternative with no local pollution in urban areas. Noise pollution, a persistent issue for airport neighboring residents, is also alleviated with the quieter operation of high-speed trains. The ability of high-speed trains to efficiently serve multiple stops is another distinct advantage. Unlike airplanes, which spend considerable time loading and unloading cargo or passengers, as well as taxiing and taking off, trains make brief stops at intermediate stations. This streamlined process significantly improves the overall efficiency and economic viability of high-speed rail services, particularly for routes with intermediate demand. Energy efficiency is a fundamental strength of high-speed trains. These trains are more fuel-efficient per passenger space offered than planes, contributing to a reduced carbon footprint. Additionally, high-speed trains predominantly run on electricity, which can be generated from a wider range of sources compared to the kerosene used by airplanes. This versatility in energy sources aligns with the growing emphasis on sustainable and renewable energy in the transportation sector. However, it is crucial to delve into the disadvantages of HSR as well. Land acquisition is often a requirement for HSR projects, leading to complex negotiations and potential legal challenges. Additionally, the susceptibility to land subsidence, as witnessed in Taiwan, can result in unexpectedly high repair costs, posing financial challenges for HSR projects. The expense associated with tunneling through mountainous terrain and implementing earthquake and safety systems can be substantial. Crossing mountain ranges or large bodies of water requires costly tunnels and bridges, or alternatively, slower routes and train ferries. Unlike airlines that can adapt routes more flexibly based on demand and profitability, HSR infrastructure represents a significant sunk cost. This lack of flexibility in adjusting to changing market conditions poses challenges for the adaptability of HSR services. Airlines frequently and assertively add or cancel routes based on demand and profitability, with over 3,000 unused routes recorded in 2016. In contrast, high-speed rail HSR may adjust its services, but the railway infrastructure itself represents a substantial sunk cost and is not as easily modified in response to changing market conditions. However, from the perspective of passengers, this can be advantageous, as rail services are less prone to being withdrawn compared to their counterparts in the airline industry. Cities not lying in a straight line presents a logistical challenge for HSR, introducing twists and turns that can significantly extend travel times compared to point-to-point flight routes. This inefficiency needs to be carefully considered when evaluating the overall attractiveness of HSR. Moreover, HSR routes require the coordination and collaboration of multiple geographies and governments. Political issues can render certain routes unviable, adding complexity to the planning and execution of high-speed rail projects. Safety is often touted as a benefit of HSR due to its predictable route. High-speed rail systems are designed to reduce, though not eliminate, collisions with vehicles or pedestrians through the use of non-grade level tracks and the elimination of grade level crossings. However, it is essential to note that, despite these safety measures, accidents can still occur. Notable incidents, such as the 1998 Enschede train disaster and the 2011 Wenzhou train collision, where speed was not a factor, serve as reminders of the importance of ongoing safety vigilance. The advantages and disadvantages of high-speed rail are multifaceted, requiring a nuanced understanding of various factors. While HSR offers compelling benefits such as reduced overall travel time, increased comfort, reliability, and environmental sustainability, challenges like land acquisition, infrastructure costs, and political considerations warrant thorough consideration. The dynamic landscape of transportation demands a comprehensive evaluation of both the merits and drawbacks to determine the most effective and sustainable solutions for the future of travel. What are you guys' opinions on this? Let us know in the comments below. Like, share, and subscribe to our channel for more interesting railway updates.